is money in an interest-bearing account. If you have an account that has some fixed interest rate, then it's like automatic to say how much money is going to be in that account after some number of periods go by. If there's a 5% interest rate, that means that every time it goes through one interest period, multiply the amount in the account by 1 plus 5%. And so if you want the amount of money after some amount of time, I mean, it's up there. Multiplied by 1.05 enough times, that's exponentiation. You also see sometimes banks advertise an interest rate, but they say it's compounded quarterly. That is to say once every 3 months. So what that means is the bank is going to take that interest rate of 5%, divide it by 4, giving, I guess, 1.25%, and then apply that rate of interest every time a quarter passes. Make sense? So let's make a quick comparison. Yeah.
Is it the same? Do you have the same?
Ooh, let's find out. We're about to do a computation. Well, let's see. Maybe intuition first. So you have these two accounts. One bearing an interest rate of 5% compounded annually. This next one compounding an interest rate of 5% compounded quarterly. Let's just see what your intuition says. There's no judgment. Many people think those ought to produce the same eventual amount of money. How many people think that annually should produce a greater return on investment? How many people want to think quarterly should produce a greater return on investment? Cool. Let's see how it works out. So, in order to see what happens, here's how we'll try to work it out. We did 10 years with the $5 and 5% interest rate right there. So let's apply this. Every quarter you multiply the amount by 1.0125. Let's try to figure out how much is in this account after 10 years. So in 10 years, how many quarters have gone by? Yeah, let's say it louder. Yeah, right. Every year, 4 of them go by. 40 in total. For each quarter that passes, you multiply by 1.0125. So, in these 40 quarters, you multiply by 1.0125 raised to the power of 40, I guess. That seem fair enough? Well, then let's figure out how much money you have after this amount of time. You have the initial investment of $5 times 1.0125 raised to the power of 40. And that's obviously not something that you're going to do by hand. I borderline wouldn't want to multiply 5 by 1.0125 once, let alone 40 times on my own. So I'll bust out a machine. If you've got a calculator, calculator along with. 5 multiplied by 1.0125 raised to the power of 40. That agree with what you're getting? Is that the same as the annually compounding result? Nope. In fact, it's a little bit better. It's 21 cents better. Wait, why did I click away? I need to actually see that number. No, it's 7 cents better. 8 cents better? Whatever, it's a little bit better. Dollar sign first. 8.22. So, quarterly one gives you a better return on investment. So first index. In fact, there's nothing special about quarterly. Like most banks don't advertise an interest rate that's compounded every 5th of a year, but that's just because a 5th of the year is like a weird amount of time to think about. But I guess it's not that weird. Like 365 is divisible by 5. It's not actually divisible by 4. Not all the quarters have the same length of time, right? The months have like weird lengths. Anyway, if you have an initial investment, P, for principal, in some account with annual interest rate R, which is compounded n times per year for any n, you do exactly the same thing. You take that interest rate, you divide it by n, so you're applying 1/n of the interest rate at a time. How many periods have passed? Well, if n of them pass per year, it's the number of years times n. So if you multiply it by 1 plus r over n times t times the initial principal of p. That seem like a sensible formula? Nice. You apply 1/n the interest rate, and maybe we'll do some color coding. You apply 1/n of the interest rate n times per year. That explains the n times t. So let's play the exact same game. I've changed the numbers from the previous ones to like maybe something that seems more sensible. Most banks with a reasonable interest rate won't let you deposit $5. Which is maybe a commentary about capitalism, and you have to have money before you're allowed to make money. Anyway, not the point of today. So you put some amount of money, $150 arbitrarily chosen, in an account with annual interest rate 7.5%, unreasonably high interest rate. You're not going to find that in the bank. That compounds, say, 12 times per year, so monthly. How much money is going to be in that account after 10 years? Let's try to work it out. Can we just apply that formula? Yeah, so go ahead and do that. I'll write down the formula. I'll wait for you all to do the computation. So the principal is 150. I'll just have to remember that it's in dollars. Times 1 plus interest rate is 7.5%. Percent literally means divide by 100. So 0.075. I want to apply that interest rate. I want to apply 1/12 of that interest rate, but I want to apply it 12 times per year. 10 years are passing. So, while being very careful with your parentheses, I don't want to do the computation. I want to wait till someone tells me what they got and maybe a consensus forms. 316.81. Do I hear a second? Cool. Did anyone get something wildly different from that? All right. Dollar sign. Ooh, in fact, let's record more digits. Give me more digits after that 81. Maybe
It'd be 8096.
Maybe one more.
9.
Cool. The reason I'm doing that is because we're going to notice something happen as you increase the number of intervals, and the something that happens will appear farther down the number. So there's the result if you compound 12 times per year. If you ignore leap year issues and you see that exact same interest rate advertised, but this time compounded daily, let's just see what intuition we have. What do you think will give you a better return on investment, monthly compounding or daily? Monthly? Daily? Cool. It's totally a guess. We don't have a good reason to believe either way. Let's see which one does better, and let's see if it does much better. And by I mean us, I mean you. I'm not going to do it. I want you to do it. once a few people have done the computation, we'll come together. Although maybe I'm being unfair. People want me to do it too? Okay, cool. So, what do we get? I bet it's somewhere around $316.80.
It's 317.
Oh, it goes up by a whole dollar. So 317. Give me some digits.
0.5250.
Nice. So it goes up by, I guess, 70 cents over a 10-year period with an initial investment of $150.
We should do that every hour now.
Well, funny you should ask that. Flip to the next page. I didn't try to break it up into number of hours. I just picked some bigger numbers. If you want to do hourly, we can do hourly. Should one of these be changed to hourly? You want to do hourly? I think people want to do hourly. All right, cool. How many hours are in a year? There's a place to begin. There's space in the margins. So, first step, number of hours per year, ignoring the issue with leap years. 8,760. Do I hear a second that looks right? Cool. I guess 365 days per year times 24 hours per day. So, if you want the amount of time, was this 10 years still? 10 years. You have the initial investment times 1 plus 0.075 divided by raised to the the number of times we compound our interest by a factor of, I guess, 24 from the previous entry. What do we get?
317. 4.
Cool. So let's compare that with the previous, 8? 3. Okay, that's... So let's compare that with the previous answer. So going from daily to hourly, hundreds place didn't change, tens place didn't change, ones place didn't change, dimes place didn't change. It went up by about 2 cents. So it is continuing to get better. But what do you think? Is this starting to stabilize a little bit? If we keep on ratcheting up the number of times we compound, do you think the total will keep going up? This pattern seems to indicate that it should, but by less and less. There's some sort of horizontal asymptote as n gets big. So if you were to fix everything constant and let n be the independent variable, I bet there's a horizontal asymptote. I bet it's somewhere around 317.54898. Maybe a little bit better than that. So here's the next thing I'd like to do. Let's ratchet up the number of periods. 8,000 is pretty close to 10,000. So let's do 100K and 1 million times per year. Do the computation. Let's see what we get. extremely surprising answer that doesn't seem in line. See if you've made any silly parentheses errors. I looked around and I saw some faces that looked like they were wincing as well. I make that comment. Do I hear a result for one or the other?
For the 100,000 one, it's 317. 2.54,991.
Nice. So it's gone up by about 1/10 of a penny from daily. Million times. I'll get you started. What are the rest of this digits going to be? Okay. So let's do it. I want this. Let's see, the initial investment was 150 times 1 plus 0.075, because that's how much 7.5% is, divided by 123, 123, divided by a million, raised to the 10 multiplied by 123.
Oh, really?
It gave you like a number overflow?
Yeah, it's a number of them.
Huh.
Either I typed it in wrong or something.
If you typed it in wrong, I should have just given you like an unreasonable answer. Because the number you're getting is like only 10 million. That's weird. Did any other people get like an overflow error in their calculator? Huh. Oh, maybe. Anyway, so what do we see? 0.5. 499,119,3381. So let's see. Same. 8 became a 9. Oh wait, I should be comparing these two. So that last one became a 9, so it went up by what, like penny, 1/10 of a penny, 100th of a penny. It went up by 8/1000ths of a penny. So the amount that's going up is decaying, even as like the jump from 100,000 to a million is like kind of big. So this should suggest that it's stabilizing somewhere. And in fact, you'll find that it does stabilize. This gives you a formula for the so-called continuously compounding interest. If you put money in an interest-bearing account, which advertises a continuously compounding interest of R for some amount of time, the amount that's in that account after time t is given by initial investment times E raised to the R times t. And I think the best way to be convinced of this is let's check it for exactly this example. We already know what the answer ought to be. It ought to be something like that. Let's apply that for this. So 150, there's the initial investment, times Euler's number E raised to the interest rate 0.075 times T. Well, best we're going to do is approximate. Well, let's see what we get. Click this button, push this over. 150 times Euler's number, E, raised to the 0.075 times 10 years. That seems pretty good. right, so let's see where it went different. So that 9 just would round that up to a 5. Bunch of zeros. So it's like this 3 ratcheted it up by about 7. 9 went up by about 9. So it didn't go up by much, and no matter how big a period you apply, you'll never get bigger than that. You'll just get real close to it. You know, that feels pretty good. Interest-bearing accounts, those just naturally produce Euler's number. In fact, this is why Euler's number is defined to be what it is. Euler's number is, by definition, the base that you get when you take a limit of a bunch of these formulas as the number of periods per year goes to infinity. Nice. Seem pretty good? Groovy. If you like, maybe I'll write down one last technical sounding thing. E is, and this is going to be some calculus words, so I'll put it in plain English in a moment. It's the limit as n goes to infinity of 1 plus 1 over n raised to the n. That's not something that you need for this class, but that's what's happening. The only difference between this and that formula is there's like an r involved. So if you imagine you had an interest rate of 100%, E would be the effective annual interest rate. Groovy. How's that seem? Nice. So what does this mean? This just means when n is really, really big, if you compute that thing, you'll get basically E. Other applications of exponential functions. Population growth seems like a reasonable model, right? If you have some population that's growing exponentially fast, so that, under what conditions does that happen? A population grows exponentially when the population is small enough that it doesn't start bumping up against any of the upper bounds on the population imposed by the environment. If you have like a smallish number of rabbits in a field that's got lots of grass, and it's not going to freeze over the winter, and there aren't predators to eat the rabbits or cars to run them over, or any of the other reasons the rabbits just die, that population of rabbits will grow exponentially. Once the population of rabbits gets big enough, they'll have like eaten too much of the grass, and then rabbits will start starving, and the population growth won't be exponential anymore. It'll be some other model which gets called the logistic model, which we won't hit, but only in the interest of time. It's not that it's anything too far. If you want to look up more reasonable population growth models, go look at the logistic model. Anyway, I'm getting myself distracted. So a population growing exponentially will be modeled with an exponential function. That is to say, that population will be given by the formula P of t is equal to initial population P0 times an exponential function. Euler's number E raised to the kt. There's nothing special about putting Euler's number E there. It's just the base that makes calculus work better, so we may as well use it. On the next page, we'll develop a different model that you can use when you don't care so much about using the base that will make calculus nicer. You have a population of bacteria growing in a petri dish. Let's suppose you start with a sample of 0.2 milligrams. Let's suppose that after 1 hour, if you just by mass determine how much bacteria is in the dish, you have 0.3 milligrams. Let's answer this question. How long will it take before you have 1 milligram in that dish? And of course, this is a mathematician talking about an example that's coming from biology, so all of these numbers should be treated as bullshit. I didn't perform an experiment, I didn't take any measurements, I wrote some numbers down. So let's see what happens. So, you have this general model that you'd like to use to answer this question. I don't have enough information to use the model to answer the question yet, but I think I can extract it. What's the initial population? How much bacteria did you start with? 0.2 milligrams. So, 0.2 milligrams. I guess I'm going to include the units. I know that at time equals 1 hour, because at 1 hour you have 0.3 milligrams. So when t equals 1 hour, the result should be 0.3 milligrams. So let's do that. So there's 0.2 from the P0 times e to the unknown constant k times, and you know what, let's include all of the units. 1 hour. Which means I guess there should be a 0.2 milligrams here. Cool. So there's this unknown parameter k. Is that the only unknown in that equation? Looks like. So you should be able to solve for it. And maybe I'll give you a choice here. You do the algebra or I do the algebra. People want me to do the algebra to solve for k? Cool. Do the algebra. Determine that constant k. I think I would like both the exact value and the decimal approximation. No, that's the wrong color. It should be black. So you want like the unit in the final answer would be interesting. So I think I'd like what unit is going next to that k. So, what do we get for k? Yeah, what units?
That's what we'll talk through. I think I want to go through the thought just to like track the units.
So, you said 0.4? Yeah. Cool. Do I hear a second for about that is the decimal approximation you get for the k? Anyone track what units you should have on that k? Yeah, I'm going to. Regardless of whether people said they knew. Let's do it. So I'm going to go through this computation and I'm going to track the units the whole time through. The way I'm going to do this is I'm going to treat the units just like they were numbers. It's not a number, like hour doesn't mean a number, it's a length of time. But you can divide and then the hour becomes per hour or something like that. And 1 milligram per milligram is just 1. So let's try to go through this. So, in solving this, maybe you erased all of the numbers to begin with, all of the units to begin with, because they were all consistent. But let's walk it through. What's the first step you did in solving? I guess you probably divided by 0.2 to get that to the other side. I'm going to do exactly that, but I'm going to put the milligrams next to it. And we'll see the units cancel, so like, if you drop the milligrams, you didn't lose anything. 0.3 milligrams divided by, well, I made it blue, so let's make it blue. 0.2 milligrams is equal to e to the k times 1 hour. And that was supposed to be an orange, but that's okay. So the thing you see immediately is 0.3 milligrams divided by 0.2 milligrams is the same as 0.3 divided by 0.2. And that like looks like an annoying division, but it's not, right? It's 1.5, and the way you can see that is, right, how do you divide by decimals? You like move the decimals over the same amount in the numerator and denominator. That's the same as multiplying both sides by 10. Yeah, so that's 3 halves or 0.5. 1.5. Nice. Cool, what next? That looks like an exponential equation. All the unknowns are inside of the exponent. So what's the trick to do? Take the log, or we write it in log-based form. They both mean the same. Apply the log to both sides. That'll cancel the e to the power. What base do I want on this log? Yeah, base e, so I really want ln. ln 1.5 is equal to k times 1 hour. And if you suppressed all the units, then in some sense you are done. I guess ln of 1.5 is that, I didn't write it down, 0.4-ish? 0.3-ish? 0.4-ish. Okay. But let's deal with that 1 hour. That case still has a 1 hour multiplied by it, so how do I get rid of that? Divide by 1 hour. So, what do I get? I get that k is equal to the ln of 1.5 per hour. And so what does that mean? That means, in some sense, that every time ln of 1.5 hours goes by, you multiply the quantity by e. That feel pretty good? And now let's get that decimal approximation. That was about like 0.4-ish per hour. Nice. We feel pretty good? And what we'll see at the end is that all the units were in hours, so if you did forget all the units, you would be just fine. But let's play the game. So I now have a model. I have the model that P of t is equal to 0.2 milligrams times E. I know what K is. It's ln of 1.5 per hour times T. And I guess if I'm putting the units in, I should put the units in. Nice. Feel okay right now? And the divide by hour now makes a lot of sense. That time is in hours, and I don't know how to raise something to a power of 3 hours. I don't know what that means. I can only exponentiate with a number in the exponent. So let's try to do this. I want to know when the population will hit 1 milligram. So that means I need to set 0.2 milligrams times E to the ln of 1.5 per hour times T to 1 milligram. Does that also look easy enough to solve? And I'll give you a choice here, like, should I talk through it or should I just wait for you to tell me the answer? Should I do any of the algebra? Cool. And once we have an answer, we'll like do something intuitive to check it, I think. And once you're settling down on an answer, compare with the people around you. Depending on some choices you might have made in terms of rounding, you might have differing looking answers. So if you do have different answers, assume that one of the two of you did something wrong. Just see if there's a choice that one of you made that the other one didn't. No, it's just like,
I don't know. I don't think this. Could I put both sides?
is the 45 telling me that's in like scientific notation or something?
I think it's a really big number.
Yeah. So with 45, yeah, it's too big. It's not going to take that long.
Yeah, it's not, no, that's what I'm thinking.
Exponentiation grows fast. At a glance, it looks like you exponentiated when you should have logged somewhere.
Like they use,
Yeah, but there's also, I also saw an E in what you typed in. And I think it should just be a log base E. Let's actually talk through it. Let's hear. So what are some answers that people think seem reasonable that they got? $3.97. So that's about 4 hours. Do I hear a second for that? Did anyone get a number that's like somewhere around that, but differing in some of the decimals? Oh, okay. Then I was hoping there would be some more controversy than that. So about 3.97. What units?
hours.
Yeah. And the per hour is tracking that for you. Because at some point you'd like multiply both sides by hours. So let's check that before we like do the walk. So from point 2 to point 3, that was 1 hour, and you multiplied by 1.5. In 4 hours, you should multiply by 1.5 4 times. That seems sensible. So let's see what that works out correctly. 0.2, let's multiply by 1.5 to the power 4. We could multiply by like 3.97, but let's just see if that works out correctly. Oh, 0.2 times 1.5 raised to the 4. That pretty close to what we wanted? And like 4 isn't exactly 3.97, so I didn't expect it to be exact. I think I believe the answer. Shall we go through the algebra? Let's do it. So, how many people, right when they began, just forgot all the units and just figured it would all work out well? That's fair enough, it will. All the time is in hours. all of the masses are in milligrams, so there's nothing to worry about. But I'm going to worry nonetheless. So, there's the equation you want to solve. What was your first step? Divide by 0.2. I'll divide by 0.2 milligrams. E to the ln of 1.5 per hour times t equals 1 milligram divided by 0.2 milligrams. Milligrams cancel. And what's 1 divided by 0.2? 5. Because you move the decimal by 1, this one becomes 10. 10 divided by 2 is 5. That's not the only way to see it, but that'll do. So what do I have? I have e to the ln of 1.5 per hour times t equal to 5. What seems like a good next step? Put it in log form. So, ln of 1.5 per hour multiplied by t hour is equal to the ln of 5. All right, what next?
Where did the other ln come from?
Which other ln? This ln?
Yeah.
This is in exponential form. All the unknowns are in the exponent.
Yeah.
I suspect that's where your walk went wrong.
Yes.
I think you maybe lost that ln. Cool. So now I see a thing times time is equal to ln of 5. I guess that means we cross divide / cross multiply to get the t on its own. So it looks like t is ln of 5 divided by ln of 1.5 divide by hour on the other side, so now it's multiplied by hours, which is what you expect. Time should be in hours. So if you just more careful with units, you will find on this problem. But that was more careful when we saw that it did more careful. Is that the answer people got? Anyone do any simplifying after this?
I changed it to the log base 1.5 to 5.
Yeah! It's a log divided by a log. The change of base formula says that that's the same thing as 1.5 in the base. That's not like a super important substitution to make. In fact, if you then ask a calculator for the log base 1.5 of 5, it'll just turn it back into this to do the computation anyway. But it's still a simplification that's, fewer symbols to it. ln base, log base 1.5 of 5 hours. Feeling pretty good? Nice. So, there's one way of thinking about exponentiation. Anything that's modeled exponentially can be modeled with an e in the base, as long as you allow for some unknown multiplier in the exponent. But that's not the only way to do it. You can also just let the base be unknown. That seems sensible. Here's another general model for exponential growth. A population that grows exponentially can be modeled by P of t equals initial population times unknown base b. I guess it better be bigger than 0 because the base is always bigger than 0, raised to the t. That seem like a reasonable plan? Let's do one real quick example, and maybe I'll be more efficient than the previous one. So here's a problem. You start with a population of 3 rabbits. After 4 days, you find that you have 8 rabbits. This rabbit population is growing unreasonably fast. How many rabbits do you expect at day 10? Does it seem like a doable thing? Yeah, I guess step 1 is figure out the unknown base. So the initial population is 3 rabbits. I'll suppress the units on this one. At time equals 4, you have 8 rabbits. So that means 8 is equal to 3 times the unknown base raised to the power of 4. That look like an equation that's solvable for b? I think so. In fact, like, you don't need to use any logs or anything to solve this. Right? I guess I'll need to take a 4th root at some point. So doing that, what do I get? I get 8 thirds is equal to b to the power of 4. How do you undo? Yeah.
Fourth root squared root? How would you say that?
Just the 4th root, right?
Fourth root of 8 over 3.
Yeah. Or, if you like, and I think I do want to do this because there will be other exponentials. Because that's how you would probably ask your calculator to do it anyway. I don't know if your calculator has a button for a 4th root. Does it? Oh, it doesn't need one. You could just raise it to the quarter power. Ooh, so how many people would want to have a plus or minus in there? Well, you're undoing a 4th power by a 4th root, so like there should be one. But why isn't there?
It's long.
Yeah, well, it's a base. In an exponent, bases have to be positive. And it's also a population growth. Like, a negative number as the growth rate would not make much sense. All right, let's use the model to address the problem. So I want to know the population at 10 days. So let's do it. That'll be 8 over 3. Oh. It'll be initial population of 3 rabbits times, I now know the base. It's 8 over 3 raised to the 1 over 4. And then I need to take all that and raise it to the 10th power. That look easy to compute? I'll simplify it a little bit before we compute it, just to remember our exponential laws. That looks like I'm exponentiating, then exponentiating again. So this will be the same as 10 over 4 in the exponent, also known as 5 over 2. So that's 3 times 8 over 3 raised to the power 5 over 2. So when you do that computation, what do you get? And you will get an answer that will seem silly. Do I hear a second? Nice. Is there something silly about that answer? What does 8.84 rabbits mean? And this is always a defect when you model a discrete population. Discrete is in it only takes whole number values with something continuous. Maybe what that 0.84 means is you should incorporate that as there's some of the rabbits are Quagars and they're going to be Boston. And so those don't count as whole numbers of rabbits. You have to do some thought about what that should mean. Yeah.
In this instance, when it goes a question on the exam, would you want us to say that it would be 3.84 rabbits, or would you want us to say round up or down?
I would be happy if you made that conclusion, then you added a sentence, because it's not totally clear whether you should round up or down. Really, what this conclusion is that this model doesn't really 100% accurately model the situation. Really, there should be something more exclusive. Except that there was an error you noticed on the thing. So don't just tell me because I'll forget by the time it matters anyway. There is a small point incentive, an extra point on the exam. If you compose an email and convince me that the answer that I provided is incorrect, and then your answer is correct.
Okay, I will do that.
Yeah. Or you can come by my office and I'll explain it. Whichever.